If you recall, yesterday we started talking about that first big question that we're going to use to help us study infinity, and as it applies to rates of change. And our first big question in calculus: what is the slope of the line tangent to a curve at a given point? We ran into the problem is that we wanted to calculate a slope, but we are only allowed to use 1 point. So we cheated and we changed it to 2 points. We picked a point that's close and found the slope, using the slope of a secant line to approximate the slope of the tangent line. And then we improved that approximation by taking our secant line and making those 2 points closer to the point that we're interested in, moving the points closer. That raises the question, how close we should make them. Should we make them? And the answer was close enough so that we could tell what is going on. Then we ran into the idea of a limit. The intuitive idea, as it applies to the example that we did, was as the change in x got smaller, approached 0, the slope was approaching 1/3. We just looked at that with numbers. We saw more zeros that I put in before the 1, or the more 9s that we threw in after the 2. The more 3s we got, it looked like we were headed towards 1/3. And with some of you have secret math knowledge, you knew that the derivative of natural log of x is 1/x, so we were definitely headed towards 1/3. But this came out as kind of an intuitive description of what's going on. As delta x got closer to 0, the slope got closer to 1/3. As delta x approached 0, slope approached 1/3. That's fine for our intuition of what's going on, and it makes sense in the context of what's going on, but it's not very rigorous. We have to define what we mean when we say delta x is approaching 0, and that causes the slope to approach 1/3. Not that we don't know what the word approach means, but what does it mean to put that whole thing together in context? As delta x approaches 0, slope approaches 1/3. What does that sentence mean? So, being math folks, being mathematicians, we have to come up with some kind of workable definition. And this is what we came up with. We, like I was there. I'm going to simplify the problem, take it out of the context of the slope that we were calculating yesterday, and just say, what does it mean to say that as x approaches c, f of x is approaching L? We're just going to look at the function, the limit of a function. As x approaches c, f of x approaches L. What does it mean to say, as x gets closer to c, f of x gets closer to L? What does that mean? And here's the definition we came up with. Once again, we, like I was there. We say that the limit as x approaches c of f of x equals L. These are the words. These are the lyrics to that symbol. Do you call them lyrics when it's the symbol? It's just the words that you use for the symbol. Otherwise, you just start spelling things like, oh, limit x. You don't know how to say arrow, so you like to say x, c, fx equals L. So don't just read the symbol. So when you see that, you're going to say limit as x approaches c of f of x equals L. This is our abbreviation for if and only if. Big indication that we're making a definition. I don't want to write for every or for all the time because that's so many letters. So we just write it upside down A. That's a fairly common abbreviation for every or for all. For every epsilon greater than 0, a backwards E. Once again, I don't want to write there is or there exists because that's so many letters. I'm just going to write a backwards capital E. That is also fairly standard as far as math abbreviations go. So for every epsilon greater than 0, there is a delta greater than 0. Then I write a backwards is an element of as a such that. This is much less common, but I was raised doing this, so now y'all are being raised doing this. If you don't like it, just remember hurt people, and that's what happens. So you're just going to be raising that. For every epsilon greater than 0, there's a delta greater than 0 such that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. We have to be able to read absolute value inequalities. We have to be able to read absolute value inequalities. This first one, absolute x minus c less than delta, means x is within delta units of c. X is within delta units of C. That's how we read this part of the statement. X is within delta units of C. So if I'm going to be within 1 unit of 10, that means X is going to be somewhere between 9 and 11. So we have this, we can say this limit exists if X is within delta units of C, forces f of X to be within epsilon units of L. That's what this absolute value inequality says here. That's how we're going to read those absolute value inequalities. This is how we should read absolute value inequalities. A lot of times we see absolute value inequalities in the context of an algebra problem, and they tell you how to get at what they refer to as the answer, which is the biggest mistake. Because it once again reinforces the notion that the answer has any kind of importance or bearing on the problem itself. I mean, that's not why we're in math class. You know what I mean? The other reason that we're not in math class to do is to have to write down all the math all the time. I don't know if you've ever been in a class, like an algebra class, like, I'll show your work. It's like, well, if you don't have to do any work and you could just write down the answer, then you should write down the answer. The point of being in a math class is to avoid writing down all the steps. You want to avoid that. That's the goal. Become so good at the steps, you ain't got to write them down anymore. That makes sense? That'd be like me giving you a driving test, have you write down the steps and getting in your car and driving off. It's like, well, make sure you list everything. Step 1, unlock door. Step 2, open door. Step 3, sit in seat. Step 4, close door. Step 5, put on seatbelt, and have you write all that shit down instead of just have you get in the car and drive off. It's like, well, clearly they know this first part. And if you like drive off and the door is still flopping open, I'm like, oh, well, clearly they don't know what they're doing. You know what I mean? So if we look at this absolute value inequality, if we do the algebra thing and we solve it, when we have an absolute value less than, an absolute value inequality in this direction, what we're saying is that the absolute value of X minus C could be less than delta, or X minus C itself could be less than delta or greater than the opposite of delta. Remember, in the statement of our definition, we've required delta to be some positive value, so it makes sense to write the inequality this way. If delta is negative, then this first part of the sentence doesn't make any sense at all. Then if I just go through and add C to all 3 parts of our absolute value inequality, here is X. It is less than delta, than C plus delta. And greater than C minus delta. That's what it means to be within delta units of C. The same thing happens with f of X is within epsilon units of L. This is requiring that f of X minus L be less than epsilon and greater than minus epsilon. This is how we get rid of an absolute value in an inequality of this type. Then if I add L through all the way through, then we find f of X has to be less than L plus epsilon and greater than L minus epsilon. Is everybody okay? Yes. No, for this, it's strictly less. Strictly less. Because we want, because of what we're trying to describe is a tolerance. It has to be less than this. So that if we could make it, if we put or equal to, it wouldn't change how the thing functions. So we just go with the more general case. Let's visualize what we want to happen. If I have so if f of x is happening on the y-axis and x is happening on the, unsurprisingly, x-axis, what we're looking for is, in the second part, we want f of x to be within epsilon units of L. So we're deciding how close we want f of x to be to L. That's where we're making a decision. Epsilon is the tolerance we choose. So I want f of x to be in this interval, where I have L plus epsilon over here and L minus epsilon down here. I want f of x to show up in this interval. Then I'm going to look at how close I can get to, I have to have how close x has to be to c to make that happen. So then I'm going to look down here and think how close to c how close to c do I have to make x to guarantee that that would happen? What we want to see, if when we're thinking about epsilon, is if we draw that horizontal bar where epsilon is. We shrink down our delta, we shrink down this vertical bar so that the function kind of goes in one side and out the other. The function should exit that, enter that intersection, crossing one of the green lines that I have, and exit that intersection, crossing the other green line. Now that function is entirely contained, that function is within epsilon units of L. To make that happen, I have this delta, that makes that happen. I could use a smaller value of delta, and it would still be true. I could use a really small value of delta. The point is, can we make this happen? If the answer is yes, then we say the limit of, as x approaches c of f of x is equal to L. So what we need is that f of x enters this intersection crossing a green line, exits the intersection crossing a green line. Epsilon is our Tolerance is the tolerance we need to hit. Delta is how close we have to make the input to C to make that happen. As x is getting close to C, f of x is getting close to L. This is how we have to define it to make sure we all know what we're talking about. This is what it means for a limit to exist. Most of the time, this is not what we're going to be calculating. There are problems where I could say, I want epsilon to be 0.1. How close do we have to be on delta? That misses the point entirely of what's going on. This is a rigorous definition for what we have as an intuitive idea. We're looking at the function and we're saying, where is this headed? More important than the definition of a limit, and this is called the epsilon delta definition of a limit. More important than utilizing this definition is having the intuitive understanding of limits. If no such delta exists, if we cannot find a delta that makes this happen, if no such delta exists, then we say that the limit does not exist. So if we choose, there's an epsilon we can choose, and there is no delta that makes this happen, then the limit does not exist. Our abbreviation for does not exist is DNE. That is a fairly common abbreviation. If you say undefined, you're incorrect. Does not exist. We have defined an answer. The answer is there is no answer. Note that does not exist is a phrase that applies to the limit. It's the limit that doesn't exist. The delta also can't be found, so the delta doesn't exist, but we're specifically saying the limit does not exist. It's the limit that's doing this not existing parts. That makes sense? I point this out specifically because you're going to say something like it does not exist. And what does it refer to? The function, the limit, the point. You're going to refer to a bunch of things, and then you're going to say it. And if it's not clear which thing it refers to, then you need to just put the limit. You just need to write down what you're referring to. Yes. So f of x enters the intersection crossing the green line. So it crosses the green line to get into this little square in the middle, and then it exits via the green line. If we cross the red line, then we're not within epsilon units of delta. F of x enters intersection. So we want to look at some limits that don't exist, and we're going to visualize the limits, and then we're going to think about this definition and why those limits don't exist. We're just going to draw some limits that don't exist. So I'm going to pick a value C, which apparently I made green. Here's one way a limit might not exist, say at this point, x equals C. Let's suppose I got some function, it's cruising along. But then I stop using this branch down here and the function jumps up. So I've got some kind of piecewise defined function. In this case, the function is not approaching any specific value. It doesn't matter that the function has a value at C, this value right here where the dot is filled in. That doesn't matter because coming from the other side, we are not getting close to that value. We're getting close to this value down here. So let's say if this happens at we are not approaching 5. We're approaching 5 from one side, but not the other. We're approaching 3 from one side, but not the other. We are not getting close to any one value on this function. F of x is not approaching 5 or 3 from both sides. Does anybody want to average these and say 4? A lot of times we hella want to average these and say 4 because that's what we do. Our default mode of thinking is to split the difference, but we are not getting closer to 4. I could say that I am getting closer to 4 with an epsilon of 1, right? I'm getting closer to 4 if I make that 1, but that's not what the different definition says. What does the definition say about epsilon? For every epsilon greater than 0. And if I choose epsilon to be 0.5, f of x is not forced to be within 0.5 units of any number. You can't just say, we'll just use a bigger epsilon. It has to be for every epsilon. So f of x is not approaching one number. So the limit, in this case, the limit as x approaches C of f of x does not exist. F of x is not approaching some value. Now we could look on either side and do a one-sided limit. Why I picked this one first. We could say as x approaches C from the right side, we're headed towards 5. We do have one-sided limits. So I could say the limit as x approaches C, if I put a plus as a superscript, I'm saying approaching C from the positive side or from the right. So this plus C means x approaching C from the right. What is f of x approaching as x approaches C from the right? Looks like we are headed towards 5. We can also write down a limit as x approaches C from the left. From the left, it looks like we are getting closer to 3. So we do have one-sided limits. But because the value that we're approaching from the right is not the same as the value we're approaching from the left, the limit doesn't exist. So because these two values, we're not headed the same place from both sides, we say the limit doesn't exist. Question? Correct. Absolutely. So if I had a value down here, like D, that limit exists. That's we're not. It's not at this weird thing that's happening. So we could say the limit here approach as x approaches this is, I don't know, what, 2? Probably 2. If I made you guess, you'd probably say 2. It's going to be called, haha, it's actually 2.17842.396. But then I would just be being a dick. Any questions? So because these are not equal, that's why the two-sided limit doesn't exist. Note that the value of the function is irrelevant in this discussion. What the function is at, what's actually happening at the function doesn't matter. We don't care about that. I'm sorry, buddy. Okay? Yes. No, because when we're thinking about the domain, if we have a function that's not defined at a point, it might just be not defined there. And everything to the left, everything is just fine. But we still might not have a one-sided limit because we might not be approaching some value. Let's look at an example of that. See, it's like the class writes itself. The next example that I was going to do. If I labeled in these example? No. So once again, I'm going to have some shenanigans going on at x equals c. So here's an example of a left-sided limit that doesn't exist. The values of the function are approaching infinity. We're not getting closer to a number. Infinity is not a number. We can't say something equals infinity. Saying equals infinity doesn't make any sense. Equals is for numbers. Infinity is not a number. When infinity shows up at the numbers club, the bounce is like, oh, sorry, you're not on the list. It doesn't let it in. It's like, oh, but I'm infinite. It's like, well, that means you're not a number. And then pi comes along, so and it waves at the bouncer, and then the bouncer lets pi in. And then he's like, oh, come on, man, that guy's crazy. He says, no, 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 we say irrational here. Thank you. So in this case, I'm just going to do like a 1 over x squared type of deal. I can never draw these symmetric, so it can't be like a 1 over x squared type of deal, but let's pretend. So in this case, the limit doesn't exist. Let me make this one a little thicker. Looks a little bit simple. F of x is not approaching any value, it's approaching infinity. So we don't want to say that the limit is infinity. We could say that the limit is approaching infinity, but only because both sides are going to the same infinity. This would be an acceptable way to express that. This would include some more information. It's saying, well, not just that it doesn't exist, but it's headed towards infinity. That's why it's not existing. We can say the limit as x approaches c of f of x is approaching infinity. This is unacceptable. Equals is for numbers. At the equals club, the bouncer rejects infinity. Saying equals infinity is completely unacceptable until it is acceptable. None of you are qualified to write equals infinity. When you win 20 in the show, you can let the fungus grow on your shower shoes and people will think you're colorful until then it just means you're a slob. So you can't do that. If you want to announce your expertise in mathematics because you're like a newly minted grad student of math, you've got your bachelor's degree in math, you might want to drop it equals infinity to see if the room is cool or not. And you're like, oh, you got to use infinity and equals together. Yeah, maybe it's cool. But if you're not sure, you say it approaches infinity. Then everybody's like, oh, you guys seems kind of pedantic. And then all the mathematicians will be like, oh, but we're mathematicians. Don't we like that? It's like, oh, yeah, but not when it's the new guy. Hey, new guy, why so pedantic? I'm just kidding. How's everybody okay? I'm going to train you in math snobbery as well. It's part of the process. On a related note, it might be that we have just a vertical asymptote, like a 1 over x style vertical asymptotes. Where we're approaching infinity from one side and approaching negative infinity from the other side. In this case, we could refer to the left-sided and the one-sided limits as approaching infinity or approaching negative infinity, but the limit just doesn't exist. There's no way around it. They both go to two different infinities. So we might, in this case, say that the limit as x approaches c from the positive side of the function approaches negative infinity, and the limit as x approaches c from the negative side of f of x approaches positive infinity, but the limit as x approaches c, just x approaches c, the best we can do is does not exist. I can't say that it's approaching some value because it doesn't mean anything to say within epsilon units of infinity. That doesn't make any sense at all. One thing to keep in mind is that what's actually happening at the point is not relevant. We care about what's happening approaching that point. What happens at the point is not relevant. We care where things are headed, not what happens when they get there. We don't care about the outcome. We just care about the approach. For example, for the function x squared minus 4 over x plus 2, that's actually not what I said. The function that is the quotient of the difference between the square of a number and 4 and the sum of a number and 2. When you say it actually in words that make you write that, it doesn't, it's terrible. English is terrible for expressing math, but that's why we came up with this shorthand. So this function is not defined. I wanted 2, not negative 2. Let me switch to 2, not negative 2. The ink is like, oh, it's too late for that. This function is not defined when x equals 2, but it's got our favorite kind of discontinuity. I can simplify out the x minus 2. I can never forget that we're not allowed to plug 2 into this function. F of 2 is undefined. When we do something like, say, this is equal to x plus 2, because I can factor out the numerator, this only applies when x is not 2. Because f of 2 is undefined. You can't just simplify your expression and patch over all these undefined bits of your function. So when we go to draw this the graph of this function, this x squared minus 4 over x minus 2, we can draw x minus 2 everywhere except for 2. So we just draw the function x plus 2 until we get to 2 where we stop and then pick it up afterwards. F of 2 is undefined. Here's the graph of f of x. But as we approach 2, the value of the function is approaching 4. So we would say that the limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to 4. The fact that the function is not defined at 2 doesn't matter. The function is approaching 4 as x approaches 2. I can get the value of the function as close as I want to 4, so long as I make x sufficiently close to 2. I can't make f of x exactly equal to 4 in this case, but that doesn't matter for the definition of a limit. Because the limit said for every positive, strictly positive value of epsilon. So you can't choose an epsilon of 0 because that is not greater than 0. But if I want the value of f of x to be within 1/100th of 4, I just need to make sure that x is within 1/100th of 2. I made it easy on myself and gave myself a slope of 1. Also makes it easier to factor and all kinds of stuff. But if this graph was steeper, let's say with a slope of 3, then to be within 1/10 up here, I'd have to be in 1/10 over 3 down here. I'd have to squeeze in my closer to x, because the function is steeper. This is the thinking behind a limit. We need to be able to say what the definition of a limit is, and we need to understand, more importantly, we need to understand intuitively how it works. We can be as close as we want to the limit, so long as our input is sufficiently close. We can make f of x as close as we want to L, so long as x is sufficiently close to C. We can make f of x as close as we want to L, so long as we can guarantee that x is sufficiently close to C. Any questions? We can make f of x as close as we want to L, so long as x is sufficiently close to C. You choose the epsilon and make sure there is some delta that fits. Right. That's going to do it for today. That's the epsilon delta definition of a limit with some examples. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.